Hello friends, we are going to discuss today corona, a self-sustained external partial discharge in power system. Let us proceed further and take a look at the roadmap. We are going to discuss concept, voltage formulae, factors affecting corona, corona loss formulae, factors affecting corona loss, methods to reduce corona loss, and radio interference and inductive interference of corona. Partial discharge can be classified into two categories, internal partial discharge and external partial discharge. In case of internal partial discharge, breakdown of air occurs inside the insulating material and it cannot be visualized externally. On the contrary, in case of external partial discharge, breakdown of air occurs externally and it can be visualized. Now, corona is an example of external partial discharge, and it is also self-sustaining partial discharge, which is basically observed in case of high voltage transmission lines. Hence, corona can be defined as a phenomenon in case of EHV and UHV AC transmission lines as ionization of air surrounding the conductors, which results into generation of faint violet glow on the surface of AC conductors, hissing noise, real power loss, tendency of the conductors to vibrate, interference with nearby communication networks, and production of ozone. Production of the ozone is not at all useful to power engineers because it is responsible for corrosion of the conductors. Well, corona can be observed in case of HVDC transmission line as reddish bits with negative conductor or by smooth bluish white glow over the positive conductor. Let us now define two voltages pertaining to corona. But before directly moving to those, let me clarify the relationship between the voltage of the conductor and the electric field intensity of the conductor by very basic laws of the electrostatics we have learned in the past. And that is, voltage of the conductor with respect to neutral is given as V is equal to small r, radius of the conductor, into log of ratio d to small r, capital D, that is the distance between the conductors. Suppose conductors are A, B, C, and if they are equally spaced, fine, say in the equilateral triangle fashion, then the distance among the conductors will be D. If they are not equally spaced, distance between them is defined as mutual GMD of the conductors. One more thing is to be recapitulated is breakdown strength of the air. Now this is the voltage at which 1 centimeter of the air becomes a conductor, that is the breakdown strength of the air, and that is found as 30 kV per centimeter. It means 1 centimeter of the air will break down when 30 kV AC voltage peak value is applied under 25 degree centigrade temperature and 76 centimeter height of mercury in the barometric pressure measurement. Fine. Thus, we will represent this breakdown strength of the air as G0, and that is equal to 30 kV per centimeter, and that is the peak value. Fine. If you want to get RMS value, divide 30 by root 2. So that is nothing, it is 21.21 kV per centimeter, right? Now think about the air which is in contact with the conductor at the surface. Now electric field intensity of the conductor will be highest at the surface of the conductor where there is air in direct contact, and this electric field intensity of the conductor is pretty high, and that is responsible for breakdown of the air just near the surface of the conductor. Clear? Now we are in a position to define critical disruptive voltage VD. It is the voltage at which partial breakdown of the air happens near the surface of the conductor and the corona starts forming. Hence, using previously defined equation of the voltage in terms of electric field intensity, radius of the conductor, and distance between the conductors, we can now formulate an equation of critical disruptive voltage Vd as Vd equal to R into G0 into log D by R. Kv, it is with respect to neutral, or it is line to neutral value. Here there are two more terms in expression of Vd. One is m0 and the another is delta. m0 is known as surface factor or surface irregularity factor. If conductor is smooth, m0 is taken as 1. If conductor is not smooth, it means it has irregular surface, say ACSR conductors. Definitely m0 is less than 1. Now what does this m0 show? If surface is not smooth, definitely at sharp edges of the irregular surfaces, there will be larger potential gradient or larger electric field intensity, and that's why the corona will happen at some lesser voltage than that of the smooth surface conductor. Fine, and that's why m0 is taken into consideration. Delta is known as air density factor. Why? Because breakdown of air in case of corona also depends on atmospheric conditions, say temperature and pressure. Delta is derived and explained in the next slide in details. Now let us define the another voltage. It is critical visual disruptive voltage. This is the voltage at which corona becomes visible. Fine. And definitely this visualization of the corona will require some larger voltage than simply critical disruptive voltage. And empirical expression of this critical visual disruptive voltage is given as Vs is equal to r.g.ln mv into delta into one more term, and that is 1 plus 0.3 upon the root of delta r into log d by r kv. This is the RMS value if G0 is in RMS. Look at the expression of Vs closely. Vs can be written as Vs is equal to Vd plus Vd into 0.3 divided by root of delta into R. It means Vs is greater than Vd just by the additional portion, this Vd into 0.3 upon root of delta R. This portion is actually derived empirically. So it is not you can say mathematically derived, it is the empirical formula. What do you mean by empirical formula? The formula which is derived based on plenty of experimentations by the person. Fine. Clear? Look at the expressions of Vd and Vs again. Here m0 is written, here mv is there. They are theoretically same. It means they are surface factors. Fine. But m0 is for Vd and mv is for Vs. Further, Vs is having two types of mv. It means two types of surface factors. One is for the local corona and the another is for general corona. Local corona means we can locally visualize the effect of the corona at some portion or at some length of the conductor. General corona means throughout the length of the conductor corona can be visualized. So mv for the local corona will be definitely less than that of general corona. Now both critical voltages we defined in the previous slides are dependent on the temperature and pressure of the air, and that's why we introduced one factor delta in both of the expressions. Now critical voltages are directly proportional to pressure of the air and inversely proportional to temperature of the air. Hence, if we consider standard temperature to be 25 degrees centigrade and standard pressure to be 76 centimeter height of mercury in barometer, we can define delta as ratio of the actual pressure B to standard pressure 76 into this 25 degree standard temperature plus conversion of degree centigrade to Kelvin will require the addition of 273. So this is 25 plus 273 Kelvin divided by the actual temperature T degree centigrade and converted that into Kelvin by addition of 273, and that will be ultimately 3.92 into B divided by 273 plus T. So this is the expression of delta we shall be using every time. Let us take a look at factors affecting corona. First, conductor diameter or size. From the expressions of Vd and Vs, we can see that both expressions contain r. R is the radius of conductor. Hence, the more the radius of the conductor, the higher will be the Vd and Vs. Fine. Second, conductor surface. Definitely, if the conductor surface is smooth, Vd and Vs will be larger compared to those conductors having irregular surface or not smooth surface. Third is the atmospheric conditions. It means temperature and pressure. We have already defined delta. So definitely Vd and Vs or corona happening or corona visualization both depend on temperature and pressure of the air. And last is spacing among the conductors or capital D. In expressions of Vd and Vs, we know that there is a term log d by r. So larger the spacing among the conductors, more will be the voltages Vd and Vs. Now let us take a look at two formulae for corona loss. We already know that corona results into real power loss in form of heat and light. Now Pick has given one empirical formula to determine corona loss, and this is given as Pc equal to 244 into F plus 25, where F is the frequency of the voltage at which line is being operated, divided by delta into root of R by D into V phase minus Vd whole square into 10 to the power minus 5 in kilowatt per kilometer per phase. Now, do mind well, this is an empirical formula for fair weather condition. If the weather is stormy, then Vd, it means critical disruptive voltage, is replaced by 0.8 Vd in this formula. So that will be the loss formula for stormy weather condition, right? Now let's take a look at one more empirical formula given by Peterson, and that formula is Pc equal to 21 into 10 to the power minus 6 F into V phase square divided by delta divided by also log at the base 10 d by r whole square into the factor f, and factor f is to be obtained from the table given in the next slide. This loss is also in kilowatt per kilometer per phase for the fair weather condition. Fine. To determine factor f, we have to consider ratio of V phase to Vd. Peterson has empirically computed f depending on the ratio of V phase to Vd as per this table. Suppose, let me give you an example. Suppose the ratio of V phase to Vd comes out to be 1.4. So directly you can take the value of f as 0.3 and substitute that in the formula for the loss computation. But suppose the ratio V phase to Vd is such a value that does not lie directly inside this table. So at that time, what is to be done? At that time, Newton's interpolation technique has to be used, and that is nothing but first order linearization technique. So actually this curve is non-linear, but we can make the curve linear between two values, between two band values. Let me give you a numerical example over here. Suppose my ratio R is equal to V phase to Vd is equal to 1.142. This value is not directly lying in this table. See, have a look. Fine. So what is to be done? See, this value is lying between which two values? Between 1 and 1.2. So these two are the band values for ratio R. And for that, the band values of f is 0.05 and 0.08. So now we can easily state my f value will be lying between 0.05 to 0.08. How to obtain that f? So it can be given as f equal to f minimum. F minimum means lower band value of f, and that is 0.05 plus in the numerator r minus r minimum. R is the computed r 1.142. R minimum is the lower band value of r, that is equal to 1 divided by r max minus r minimum. R max is upper band value of r for the given interval. Fine. And r minimum is lower band value of r into or multiplied by f max minus f min. F max, that is the 0.08 and f min is 0.05. So when you put all the values, you will get f is equal to 0.0713. This is the value of F for ratio V phase to VD equal to 1.142. This is how we can use interpolation technique to obtain this F. Now let us see factors affecting corona loss. First, frequency of the voltage. Definitely corona loss will increase with frequency of the voltage, and that can be visualized from the expressions we have already seen of the corona loss. Second, conductivity of air. Definitely higher conductivity will result into larger corona loss. Third, conductor diameter. Larger the diameter of the conductor, definitely electric field intensity is lesser, and that's why the corona loss will be lesser. Next is load current. Now this is the case where there is a possibility of formation of ice or dews on the surface of the conductor. Here in such areas, when load current increases, definitely it will rise the temperature of the conductor, and that's why that temperature will definitely melt the dews formed on the conductor, and that's why corona loss will reduce. Next, conductor surface condition. Definitely irregular surfaces will give rise to the corona loss. And the atmospheric condition. We know stormy weather will be having larger corona loss than that of the fair weather condition. And one more parameter is definitely system voltage itself. Larger the system voltage, more will be the corona loss. That is quite natural. But there is a limitation of going for larger and larger voltages from the transmission line design point of view. Now let us see methods of reducing corona loss. First, by increasing conductor size. It means by increasing conductor diameter, that will result into increase in VD and VS, and hence corona losses will be reduced. Second, by increasing the spacing between the conductors. So when capital D, it means spacing among the conductors, is increased, definitely VD and VS both will increase, and hence corona losses are reduced again. And last, by bundling the conductors and using hollow conductors, it will also reduce the corona loss. Now let's take a look at one more aspect of corona, that is radio and inductive interference. Corona discharge normally emits radiation, which is normally introducing noise signals into communication lines if communication lines run parallel to transmission line. Now this radio interference is actually measured, or it is considered in terms of field in microvolt per meter at a distance from the transmission line, and this is only significant if the transmission voltages are more than 200 kV. And amplitude of radio interference level in microvolt per meter is inversely proportional to frequency at which interference is being measured. In short, we can state corona is responsible for generation of electromagnetic as well as electrostatic fields, which further result into production of induced currents and induced voltages respectively in neighboring communication lines. So that's it. Thank you. Stay blessed, happy and safe at home.